All right. So it's been a long time, I know, and everybody is, I'm sure, freaked out about the pandemic, but hopefully everyone is staying safe. And we are going to continue on with the semester as best we can. So today's lecture is going to be on binary heap. Now, to remember where we were last time, we had done a binary min tree in order to implement a priority queue. So to remember, a priority queue has the minimum item or maximum. You can do it either way, but it has the minimum item. We'll call it the minimum item. The minimum item is always at the root of the tree, and then the left and right children of the tree are always balanced, and that's the key for making a binary min tree work well as a priority queue. So a priority queue, remember we're trying to NQ and DQ items where each item is associated with some sort of priority, some sort of value, and we always want whenever we take something out of the priority queue, we always want the smallest item. So what we did is we basically took the same approach that we did with the binary search tree, but we used different invariants. The invariance of our binary min tree was that the root was always the minimum item, and that the left and the right subtrees, the left and the right children, were always balanced. Where in this case, what we're saying balanced is that the height of our left child and our right child, our left child tree and our right child tree, their difference in their heights is at most one. There can never be more than one difference in terms of how tall those trees are. Given these invariants, we were able to show that we can NQ an item into a priority queue implemented as a binary min tree with order log n steps, and we could DQ the minimum item in order log n steps. The dequeuing operation, we know where the minimum item is. It's always at the top, and so that's an order 1 operation, a constant time operation to find the minimum item. But then we needed to fix the tree, and so we needed to take one of our children or something from one of our children and promote it back up to the root. And so fixing the tree might be an order log n operation. So overall, dequeuing was an order log n operation. And so if we do this for n queuing and dequeuing operations, if we have n items overall that we're going to put into and take out of our priority queue, then we expect our overall performance to be order n log n. And the key to why the binary min tree as an implementation of a priority queue works well is because the subtrees, the left child and the right child, are always balanced, right? And that is why we are able to have this guarantee that the worst case performance of NQing and DQing was going to be order log n. That's not necessarily true for the binary search tree, because remember, the binary search tree, the invariants are different. The invariants for a binary search tree are that everything in my left tree is smaller than the value at the root, which is smaller than everything in the right tree. And so a binary search tree, the shape of a binary search tree depends on the specific sequence of inserts. And so if we insert things into a binary search tree in a bad way, or in a suboptimal way, we might end up with a very, very unbalanced tree that in the very, very worst case just turns right back into a linked list, right? And so we couldn't guarantee that our performance for a binary search tree was going to be order log n at all times. Instead, we got average case performance that was good for a binary search tree, assuming that the binary search tree had a reasonably balanced shape. But there was, given the way we define a binary search tree, we couldn't guarantee that the shape of the tree was going to be balanced. And a binary min tree does guarantee that balance, and therefore we get we're able to get a worst case performance for n queuing and d queuing to be order log n. even though a binary min tree is balanced, it grows in a kind of odd fashion if you kind of think about it. So I'm going to switch over to a little sketch pad here. So if we think about how a binary min tree grows as we add each insertion, remember what happens is at every, whenever we insert, we start at the root and we look at our children and we insert into either our left child, or we add a node basically into either our left child or our right child, depending on which one is shorter. And if they happen to be the same height, we just break a tie arbitrarily by going left. Well, if you think about what happens when you start to add nodes into a priority queue that's implemented as a binary min tree, we start off with our first node, which becomes the root of our binary min tree. And then the next node will add one to our left. And then the next insert, because our left child from the point of view of the root is taller than our right child, will end up going right. And then the next insert will go left at first, and then we'll go left again. And then the next insert will go right because our left tree is taller than our right tree. And then once we go right once, we'll break the tie by going left. Then the next insert, because technically these two, the left child and the right child from the point of view of the root, are the same height, we'll start off by going left, and then we'll add one, we'll end up filling in this right here. And then the next insert, you would think that we would want to put, fill in the tree over here in order to be perfectly balanced. But that's not what's going to happen. If you think about it, the next insert after this, at this point, we start off from the point of view of the root, and we can see that our left subtree has a height of 2, and our right subtree also has a height of 2. And so even though there's this empty spot over here that we could fill, that's not the spot we're going to fill. We're going to end up putting in, we'll end up going to the left first, and then the left again, and then ending up putting something over here, right? Now, at that point, the next insert, that's when we'll see that, we have a difference in heights between 3 and 2. And so we'll go right. And then that's when we're going to end up filling in this little bit here. And then the next insert will go right. And then because now everything is balanced, we'll go left and then left again. And then the next insert after that, we'll see that, our left side is 3 and our right side is 3. And so we'll end up first going left, and then we'll see a difference between, at this point, once we're here, we'll see a difference, and then we'll end up adding something over here, right? And then after that, we'll end up, let's see here, we'll end up adding something over here. No, not quite. After that, we'll end up adding something over here, and then here, and then at that point, we'll go here, and that's when we'll come back to the right-hand side and start filling it in, and so then we'll end up filling that in, and then that in, and then that in, and then we'll end up filling that, going here, and now we'll end up back onto our left child. And so, yes, it remains relatively balanced, but it fills in the tree in this weird pattern where it prefers going left, and so it kind of pushes all our left branches down one if it can before it goes back and backfills all our right branches. That's fine. I mean, I mean, there's nothing wrong with that in the sense that we'll still end up with our invariant, which is our left child and our right child are at most a difference of a height of 1. But it's kind of this uneven filling of our binary tree. Overall, it's relatively balanced, and so we're able to get the performance we want. But it does fill the tree in this kind of odd way. If we think about a more natural way of creating a balanced tree, you might think, I mean, it makes more sense to kind of fill in a binary tree from left to right as we go down from one level to the next, right? So if we always fill a binary tree from left to right at the lowermost level, then the tree will always be balanced. And this kind of tree, which is filled completely from left to right, one level to the next, is known as a full or complete binary tree. In this case, there's only one possible spot that could have a left child without a right child, because we're going to fill it in, kind of going from left to right, one level at a time. So if this is our full or complete binary tree at some stage, then the next node we would want to add in order to remain full or complete would put the node here, right? So, kind of going, marching along the bottom of our binary tree, adding leaves along the bottom for the next possible level. And then, then we'd end up with another node there, and then finally completing the level, and then, then start on the next level after that, right? So that would also provide us with a balanced binary tree, and it kind of fills that binary tree in a more even manner from left to right, one level to the next. In addition, it turns out that this gives us a very efficient way of storing this tree and manipulating this tree that does not require us to create a structure with a specific, a recursive structure with a recursive left tree and a recursive right tree. Instead, we can imagine numbering these nodes in the full binary tree in breadth first order. Right? So if remember, breadth first order means we start at the top and then we visit each level of our tree going from left to right. So if you imagine numbering our nodes in a full tree, right, or a complete binary tree, starting at the top, then we start off with the root as our node 0, and then at the next level, starting from the left, we end up with node 1, and then node 2, and then again 3, 4, 5, 6 for the next level, 7 through 14 for the next level, etc., etc. Right? So if we think about a full binary tree with nodes numbered according to their position in the tree, like in a breadth first order, there's a specific relationship between a particular node's number and the numbers associated with its children, right? So node 0 has children 1 and 2. Node 1 has children 3 and 4, while node 2 has children 5 and 6, and so on and so forth. And there's a simple function for expressing the number of your left or right child's node number given your number, right? And basically what it is your left child is your number times 2 plus 1, and your right child is your number times 2 plus 2. So if node 0 is the top of our tree, then the left child of node 0 is 0 times 2 plus 1, or node 1. And our right child is 0 times 2 plus 2, or node 2. And this relationship holds all the way down as long as we fill in our binary tree left to right, one level to the next, right? So from 1, we get, 1 times 2 plus 1 is 3, and 1 times 2 plus 2 is 4. 2 times 2 plus 1 is 5, 2 times 2 plus 2 is 6. Etc., etc. So 4, for example, 4 times 2 is 8, plus 1 is 9. 4 times 2 is 8 plus 2 is 10. And so if we think about a complete binary tree in that way, it turns out that instead of storing our tree as a recursive tree structure, we can simply store our tree in a list. And the indexes of the list, the indices of the list are our node numbers, and we can find our children simply by taking our index and calculating the index of our left child or our right child. So here is a full binary tree with 15 nodes in it, right? That has been evenly filled from one level to the next. And we can see that we could store this tree simply as a list of 15 nodes or 15 values, right? So node 0, that's always our root. And then when we want to traverse the tree, if we want to go left, we simply take the index that we're at, multiply by 2 and add 1, and then that gives us, the index of where our left child is. And if we want to go right from there, then we can take that, we can take node 1, multiply by 2, and add 2, and that gives us to node 4, which is, our right child. And let's say we want to go right again, then we can take 4, multiply by 2 to give 8, and then add 2, and that gives us node 10. So we can take this this tree structure and we can actually store it just as a list of nodes in an in an ordered list with index numbers, and we can still traverse up and down the tree using these index numbers because we know the relationship between the parent index number and its left child index number and its right child index number, right? We can also identify a node as being a leaf or not by whether or not it has a left index, which is within the bounds of the list. In other words, if the left index of a particular node, if the left child index at a particular node is larger than or equal to the size of the list, then that node has to be a leaf, right? So for example, 8 here is a leaf, and we know it's a leaf because the index of its left child should be 8 times 2, 16 plus 1, 17. But 17 is longer than how long the list is. And since I know how long the list is, and I know what node index the left child is supposed to be, if I don't have a left child, then I know that that node number must be a leaf, right? And so, that's so that if we're able to think about a full binary tree with nodes numbered in this manner, then we have this really efficient way of storing the tree just as a list of nodes or a list of values. And that, in effect, is a binary heap. Okay, so a binary heap is a full binary tree of values stored as a list with the following invariants. A parent item is always smaller than either of its child items, right? So it's like a binary min tree in that a parent node, the value at a parent node is always smaller than the value of either of its left children or right children, right? And the left and right children are found at the parent index times 2 plus 1 and the parent index times 2 plus 2, right? We can travel up the tree by calculating the parent index, right? So if we happen to be at a node and we want to go up the tree, then we can calculate the parent index very easily. The parent index is simply of index I is simply I minus 1 divided by 2, right? We know that an item is a leaf if the left child index that should be associated with that item is out of bounds. And we know where the root is because the root is always item 0. Right. So now we can use this binary heap as a priority queue by enqueuing and dequeuing into this heap structure in the following way, right? So to enqueue a new item into our binary heap and to keep our heap invariants, right? So what's our heap invariants? Our heap invariants are that every node in our heap, right, or every value in our heap is smaller than either of its child values, right? And so to enqueue a new item into our binary heap, all we do is we add an item to the end of the list, and then we bubble up. Where what bubble up means is we look at that new item that we added, and if as long as and we compare the value of the item at that index with the value of the item at its parent index. So we set the current index to be size -1, the one we just added, and while we're not at the root yet, while we're still somewhere down below, in the tree somewhere, right? So where we're not at the very top of the tree, we know where the top of the tree is, that's index 0. So while the current index is not 0, we calculate the parent index of our current index, and that's a simple current index -1 divided by 2. And we compare the value stored at the current index and the value stored at the parent index. And if the invariant is broken, if the parent is bigger than what is at the current index, we swap the values, right? And that fixes the invariance. And then we set the current index to be the parent's index, and we repeat this procedure until the current index ends up being the root, right? If at any point the current index and the parent index are correct, right? The parent index is the value at the parent index is smaller than the value at the current index, then we're done. Our invariants hold and we can exit the loop. And now we know that we have our heap structure with all of its invariants correct for the entire tree, right? And so basically a binary heap is a binary tree. It is a tree that is represented as a list with the binary heap invariance. The parent is always smaller than either of its children, maintained, right? So it's going to be a little bit easier if we see an example of enqueuing. So I'm going to switch to the little pad again. All right, so what does this look like, right? So here we are. We're going to start off, and we're going to add numbers into a heap, right? And remember, we're going to store these as just a list, right? And the index of the item in our list is going to represent our node number, right? The location within our tree that we're storing the item. So we'll start off with our empty list, right? And so that's so here our list is. So here's what our heap looks like at first. Our heap, right, is going to be empty, right? And so let's say we're going to insert the value 7, right? So so right now our heap is empty, right? Our list is empty. So we add the value 7 to our list, and so we end up with a value 7. So this is index 0, and so I'm gonna let's see here. I'm going to put index numbers as red. So this is index 0 has value 7, right? All right. So now let's insert, let's say, value 12, right? Okay. So we're going to right. So we're going to add a new item to our list, right? So we're going to add a new item to our list. So that's value 12. The index associated with that list, with that value, is index 1, right? So this is index 1, okay? And we start off, right? So once we add it, and then we we start off with we set our current index to be 1, right? So we start off at 1 and we say, okay, what's our parent index? Well, 1 minus 1 is 0, divided by 2 is 0. So the parent of 1 is 0, and so then we look at the what is in index 0, and that's 7. And we look at what's in index 1, and that's 12. And that's the right order, right? My parent is smaller than my current, and so I'm good to go. Now let's see if we add something like 9, right? So now if we're going to add 9 to our heap, then we add to our list, right? So then we add 9, right? That is index 3. Switching colors is kind of a pain, so I'm going to stop doing that, right? So this is index 3, or 2, I'm sorry, index 2, right? And so we can look and we can say, okay, what's the parent of index 2? Well, the parent in index 2 is 2 minus 1, 1, divided by 2, so 0. And so we look at what's in the spot 0, and we compare what's in index 2 versus what's in index 0, and we see that, hey, our invariant holds, no problem. My parent is smaller than my current index, and so I'm good, right? So now let's add something that's going to cause us to bubble up. So let's say now we're going to add the value of, okay, let's add something really small so that we bubble all the way up. So we're going to add the value of 4, right? So we add to our list, and inside that value is 4, right? And we start off, our current index is going to be 3, right? That's our current index, right? And the parent of our current index is 3. We calculate the parent. The parent index is going to be 3 minus 1 divided by 2, right? That's going to be equal to 1, right? So then we look and we compare what's in our current, right? That's 4, and what's in our parent? That's 12. There is a problem, right? So there, our invariant no longer holds. So we swap, right, the values between our current and our parent, right? So now we end up with, right, we put the 4 there, and then we put the 12 here, right? And now we set our current to be our parent. So now our current is going to be 1. And we recalculate our parent. And our parent is now 1 minus 1 divided by 2, or 0. And now we examine what's inside our current index, that's 4, and what's inside our parent index, that's 7, and we see, again, our invariant is broken. The parent is bigger than the child, and we know that it needs to be the other way around. So our current index is 1, our parent index is 0, and so the invariant is broken because what's in current index 1 is 4, and the value that's in parent index 0 is 7. So we're going to swap those two values. So this becomes 7, and this becomes 4. Our current index becomes our parent index. So that becomes 0. And our parent index, we're done, actually, because our current index is at the top already. And so now our procedure is over, and we can see that now we've fixed all our invariants. So this list of values is equivalent, right, is representing a tree where we have 4 at the top, and 7 over here, 9 over here, and 12 over here, right? So let's add another value. Let's add, let's say a value of, let's see here, what's a good value to add? Let's add 6, right? So again, we can, I'm going to go ahead and erase these index numbers. If we're going to add 6, we start by adding a new value to our list, 6, and we set our current index to the end of our list, right? The value we just added, which is 0, 1, 2, 3, 4. So current is 4, right? Remember, this current represents not the value, but the index, right? And the parent index is 4 minus 1 divided by 2, so that's 1, right? And we compare what is in index 4, that's 6, and what is in index 1, and that's 7, right? And so we swap. And so essentially what we've done is when we add 6 to the end of the list, it's as if we're adding 6, we're adding a node, or filling in a node into our full tree. And when we compare, when we calculate the current index, right, that's like, having a reference to the node we just added. And when we calculate the parent index, that's like finding which node is storing, having a pointer to our parent node. And so we compare 6 to 7, and we see that those are that invariant is wrong, so we need to swap those two, right? And so by swapping those two, it's the same thing as if we're in our tree taking our value and moving it here and swapping it with its parent, which is moving down here, right? So we swap those two, right? So we're erasing that, and we're putting the 6 here and the 7 here. And then we update our current, right, to be our current index to be the parent index 1. And now the parent we recalculate as being index 0, right? And so essentially we've added, it's as if we added a node and we're bubbling up, fixing the invariant as we go along, right? Now we're at this point here where, that's where we're looking, right? So that's where our current index is. Right, our current index is looking at that item here. It's as if we're looking at this node here in our tree, and we calculate our parent. And that's, parent is now 0. It's like the same thing as looking here, and we're comparing these two, the values at those two nodes, and we see that, that invariant works, right? That invariant is holding correctly. The parent, the value at the parent is smaller than the value at the current, and so we can stop bubbling, right? We don't have to go up any further, right? Let's add one more just to make this complete. Let's add the value 0, right? Or the value 1. That'll go all the way to the top, right? So adding the value 1 to our heap, we add it to the end of our list, right? Conceptually, it's like adding in the next node in our tree with the value 1. Then we set the current index to be the index of that node, which is 0, 1, 2, 3, 4, 5. Right? That's like having a reference to that node right there, right? And then we calculate the parent node, right? So the parent node is going to be 5 minus 1, 4, divided by 2, 2, right? And that's like having a reference to that node there, right? And we compare the values at those nodes and see if the invariant is broken. The invariant is broken, so we swap these values. Let me put the 1 here and the 9 here. That's like swapping these nodes and moving the 1 here and the 9 here. And then we set the current index to be the parent index. And the parent index we recalculate as the current index minus 1 divided by 2. So that's going to be 0. And so now our current index is where the 1 is, and the parent that we're looking at happens to be the root. And again, we see that our invariant is broken, right? The value at the parent node is larger than the value at the current node, so we need to swap. Which is in the tree as if we swapped the values here. And now we set our current node, our current index to be the parent index. So the current node is now 0. And because we're at the top of the tree, we're done. And so the procedure is over. So a heap, a binary heap, is really just a full binary tree, right, that is being filled in from level to level, left to right, and stored as a list of values, where we can travel the tree by calculating an index into the list that is associated with that position in the tree. All right. Going back to the slides. Okay, so to take something out of a binary heap, we know exactly where the small item is, right? So remember, a binary heap is an implementation of a priority queue where the invariant is always that in the tree, the value at a particular node is always smaller than either of its children, right? And so the smallest item is always at the root. Well, in a binary heap, the smallest item is always at the root of the heap, and the root of the heap is always the index 0, right? So the first item in the list is always the smallest item. It's guaranteed to be the smallest item if we've been maintaining our heap invariant. So in order to take something out, in order to dequeue out of a binary heap implementation of a priority queue, we simply bubble down. We basically take the value from the index 0, right? We take that value, and that's going to be the value we return from our dequeue operation. And we take whatever is the last thing in the list, and we move it to be the first thing in the list. We basically take it out, we remove the last thing in the list, and we promote it to be the root. And now we fix the invariant starting from the top going down. So the algorithm for bubbling down is after we've removed the root to be the index 0 item to be the thing we return, we take whatever is at the end of the list and we move it to be the first item in the list, right? We copy it into or put it into the first item in the list. And then we set the current index to be 0, the root. And while the current index is not a leaf, in other words, while we have children, right, then we do the following operation. If we have both a left child and a right child, how do we know if we have a left child or a right child? Well, we simply calculate the left index and the right index. Our left index is the current index times 2 plus 1. Our right index is the current index times 2 plus 2. And as long as both of those are valid indices, that both of those are between 0 and the size of the list minus 1, then we look at those two values in those two spots and we figure out which one is smaller. if the value of what's at the current index is smaller than either of than our smallest child, then we're done, right? Because our invariant holds. But if not, then we simply swap whatever is at the current index with whatever is at the index of our smallest child, and now we set our current index to be the index of our smallest child. That's what we do if we have both a left and a right, right? If we only have a left, right, and that might happen if we're near the bottom of the tree, if we only have a left child, then we just look at the left child, right? And we see if the left value is smaller, then we swap our current index with our left index, and then move our, and then take our current index and make it our left index, and then otherwise we're done. And we keep doing this. We bubble down until we end up at a leaf. Once we're at a leaf, we're done because there are no more children, and so the invariant holds for naturally, right? So again, we can kind of go to the iPad in order to see how this works. All right, so let's say we already have inserted a whole bunch of items into our heap. And so let's see here. Let's say we have a heap, and the heap has 1, 2, 3, 4, 5, 6, 7 items in it, right? And let's say so the root item is, let's say, we'll say is item 4, and then 9 and 6, and then these two have to be bigger than 9, so we'll make it 12 and 15, and then these two have to be bigger than 6, so then let's say 8 and I don't know, 10. All right, so let's say this is our heap at the time that we're about to take something out of it. We're going to dequeue. So remember, this list of values corresponds to a tree that looks like this, where we have 4 at the top, and then 9 and 6, and then 12 and 15, and then 8 and 10. And we can see that, our invariants hold, right? At every point in the tree, right, we have the value at that point in the tree is smaller than either of its children, and so on and so forth all the way down the tree. Okay, so now let's say we want to dequeue the smallest item out of the heap. Well, we know where the smallest item is. It's 4, right? It's at the very beginning. So we go ahead and we kind of, take 4 as our result, right? That's what we're going to return. And then we move 10 to be, we take the thing that's at the end of the list and we move it to the beginning. And then we make our list one smaller, right? And now we have to fix our heap, right? So before we can return 4, we have to fix our heap. So we start off with a current 0, right? Where this is our current index. And we look and then we calculate what our left index is and what our right index is. Where our left index is current times 2 plus 1, so that's 1. And our right index is current times 2 plus 2, or 2. So now we look at what's in, index at our current index, right? That's here, right? And we compare it to what is in our left and what is in our right, right? So this is our current, this is our left, this is our right, right? And we basically say, okay, which one's smaller? First of all, we say, okay, our left and our right index are both valid, right? They're both inside our list. They're both valid indices for however long our list is now, right? And so we look at our left and our right values and we see which one's smaller. the one in our right is smaller, right? Because it's 6. And then we compare that to whatever's in current. And in fact, 10 is bigger than 6. So far what we've done here is we've essentially, like if we look at our tree, it's as if we've taken our value 10 and moved it up to our root and then eliminated this last node, right? And now we are, our current, the current node that we're looking at is here, and then we have our left child and our right child, right? And so we say, our right is smaller than is the smallest of our two children and is smaller than what's at our root. So we're going to swap our current with our right, because that's the smaller of the two, left and right. So we'll swap these values and put 6 here and 10 here. And now we'll update current to be our, the right index. So now we'll make current 2, right? It's as if we're now moving down the tree, right? That's our current now. So we're moving current to be there. And now we're recalculating our left index and our right index. Well, our left index is our current times 2 plus 1. So 2 times 2 plus 1 is 5. And our right index is 2 times 2 plus 1 of 6. Okay? Now, we'll notice that 5 is a valid index because our list has 0, 1, 2, 3, 4, right? It has 6 items in it. So our left index is looking at this one right here, right? But our right index, that's invalid, right? So there's nothing there, right? Because our right index should be 6, but our list doesn't have a index 6 item, right? So that's okay. That just means that we only have one child, right? And so if we look at the tree representation of our heap, we can see, that it's kind of obvious that we have a left, but we don't have a right. But that's okay. We just make sure that, okay, if we don't have a right, then we just ignore a right. We just look at our current and our left to make sure our heap invariant holds. So we look at the value that's in our current index, it happens to be 10, and the value that's in our left index, that happens to be 8, and we see that, oh, no, in fact, so after our operation, from before, our situation's like this, right? And so we see that 10, in fact, is bigger than 8, and so we need to swap. So we swap these values, which is the same thing as swapping these two nodes. And then we update current to be the left index, the thing we swapped with. And then we recalculate our left and right indexes. Well, our left index should now be 5 times 2 plus 1 of 11, and that's well past the end of our list, so there is no left, right? And if there's no left, there's certainly no right, and so there is no right. And if there is no left or right, that means our current index is a leaf, and we've gotten down to the bottom of the tree, and so our operation is done. Our dequeuing operation is done, and now we can, right? So all of this is no longer needed, and now we can return that 4 that we took away from the root at the very beginning, right? All right. So if we want to do this again, so let's say we're going to dequeue another item out of our heap, then we can do this whole process again, right? So we start off with current index of being 0, right? We take whatever is in the root, the first item, and we put it aside as the thing that we're going to return. We take the last item and we take it out of the list and we put it at the very beginning. Right? And so that's in the tree view, it's as if we if we moved this node from here and moved it up to the top and replaced our root, right? And now our current is looking at the root, and we calculate the index of our left and our right child. So in this case, our left is going to be 1, and our right is going to be 2. Those are both valid indices. So we're looking at left and right. We see which one is smaller. It happens to be right. And we compare what is at our root with what is at our right. And we see that, in fact, our invariant is broken. So we swap those values. Which in our tree view is as if we swapped these values. All right? And we update our current index to be the index of the child that we swapped with, which in this case makes current is going to make current 2. And then we recalculate left and right, right? And so left turns out to be, well, left is going to be 2 times 2 plus 1, which is 5. 0, 1, 2, 3, 4, 5. That's an illegal index, so that doesn't work. And if our left is illegal, then our right is illegal, which means that we must be at at a leaf, and so we're done. And we return that value that we pulled out of the root to begin with. Right. So the beauty of a heap is that we can store it very efficiently as a list, and we can manipulate it very efficiently simply by calculating indices in order to move up and down the tree, and we can fix our invariance simply by swapping values and either bubbling up if we are adding to the end and fixing the invariant on the way up to the root when we enqueue items to the heap, or taking the root value out of the list, moving the end of the list back to the root, and then bubbling down, fixing the invariant going down toward the bottom of the tree if we are dequeuing items out of the list. So that's how, because a heap is so efficient and so easy to store and manipulate, we never use binary min trees in order to implement priority queues. We always end up using binary heaps in order to implement priority queues because of how easy and nice this representation is. Okay, so how well does a binary heap work? Well, to enqueue a binary an item into a binary heap is order log n in the worst case. And the reason why is because the number of swaps you'll have to make is related to the height of the corresponding tree that heap represents, right? And so just like a binary min tree, a binary heap has order log n enqueue worst case performance. It turns out that the average case enqueuing performance is actually constant time. Now, I'm not going to go through the analysis on this because it's a little complicated and more complicated than is appropriate for this particular class. But when you take Comp 550 you should end up seeing the analysis of enqueuing into a binary heap and being able to calculate its average case performance as being constant time once you get into that in that class. But we won't go through that analysis here because it's somewhat involved. But trust me, right? The average time in enqueuing performance for a binary heap is actually a constant time. But even in the worst case, it's only log n, right? Dequeuing is log n, again, worst case, and because we're always taking the top item, right, the root, that's the item we're dequeuing, and then we're always moving the last item from the heap. We're always promoting it to the root and then bubbling down in order to fix the invariant. And generally, that bubble down will start at the root and go all the way down to the bottom of the tree, and so that's a log n operation. To look at the minimum item without taking it out of the heap, that's a constant time operation because we know where the minimum item is. It's always an index 0, right? Now, if I'm trying to find a specific value in my binary heap, that's an order n operation. And this is where we highlight the difference between a binary heap and a binary search tree. A binary search tree allows you to find an item in order log n average time if it is reasonably balanced, because at every point you're able to, again, this assumes your binary search tree is balanced, but if you do have a binary search tree is balanced, then you can find a specific value pretty efficiently because you're constantly eliminating half of the values, right? Because in a binary search tree, you know that everything in your left child is smaller than the value at the node, at the root, which is smaller than everything in the right child. And so you know which direction you have to look in order to find the value you're looking for. And you don't have to look at half the values. And that's why in a balanced binary search tree, you'll get good order log n average time. Now, the worst case for searching and for enqueuing and dequeuing operations in a binary search tree is order n, right? Because in the worst case, if your binary search tree was the result of inserting a bunch of items that were already in order, then you're going to end up with a very unbalanced tree that essentially looks like a linked list, and so then you're going to have to go all the way down through every item, right? So if it's balanced, your binary search tree has good performance, but it might not be balanced. A binary heap provides worst case order log n time for enqueuing and dequeuing operations always, right? But only because it doesn't keep things in order, right? So the binary heap is great for things like priority queue, where you're always looking for the smallest item, or possibly the largest item, either way. So then you always know where that smallest item is. It's always at the root, and so you can get to the smallest item very quickly. And because you can rely on we can use that the invariance doesn't have to be as strong. The invariant for a binary search tree is that everything to the left is smaller than what's at the root, which is smaller than everything that's on the right. In a binary heap and a binary min tree, the invariant is a little bit more relaxed. The root only has the thing at any given node only has to be the smaller than either its left or its right. But we don't have to have everything in the left be smaller than everything in the right. So some things could be on either side, right? So by taking advantage of that slightly relaxed invariant, we are able to implement a priority queue much more efficiently with the binary heap, right? But if we are, and that gives us quick and easy access to the smallest item always. But if we're looking for a specific item, a specific value, and trying to see whether where it is in our binary heap, or if it exists in our binary heap, then we can't necessarily eliminate the left or the right child. We have to look in both places because it could be in both places. And so we might have to visit every node if we're looking for anything other than the smallest item. Okay, so we can actually use a binary heap in order to sort a whole bunch of items, just like we could a binary search tree. Basically, we just enqueue n items into a binary heap, right? Every insert is order log n, and so that's order n log n operations. And then we repeatedly dequeue the minimum item, right? So we insert all our items into we enqueue all our items into our binary heap, and then we just dequeue them one at a time, getting the minimum item back out each time. So then we get them all back out in sorted order. Every dequeue is order log n, and we'll have to do n of those. And so that's order n log n. And so overall, to sort using a binary heap, we have order n log n operations to put everything into the heap, and then order n log n operations to take everything out of the heap in order. And so we can actually use a binary heap to sort in order n log n time also. Sorting in n log n time is kind of a lower limit for sort as an algorithm, and there's no real good way of sorting any faster than order n log n unless you know something more about the distribution of your values, or it's something less than arbitrary values. So if I build a heap by enqueuing n items, then it's going to take me order n log n time in order to build the heap. But it turns out that we actually have a more efficient way of building a heap if you have all the items in advance, right? If you have all the items in advance, you can actually build a heap from those items in order n time. And so the algorithm for an efficient heap build is you start with a list of all the items in some random order, or whatever order you have them in, so that the invariant may not be hold. And then the algorithm goes as follows. You start off with the size. If the list is if the size of the list is 1, then you're done, right? If you only have one item in your list, then the invariant holds by definition, and there's nothing to check, there's nothing to do, and you're done, right? So that's kind of a base case, a degenerate base case. But if you have more than one item, you set the current index. The algorithm works as follows. You set the current index to be the parent index of the last node, right? So you don't have to look at any of the leaves. You're looking for the first node that is not a leaf, and that is always going to be the parent of whatever the last node is. You know what the index of the last node is. That's just the size of your list minus 1. So the parent of the index of the parent of the last node is the size of the list minus 1. That's the index of the last node minus 1, and then all of that divided by 2. So that turns into the size of the list minus 2 divided by 2, which is simply the size of the list divided by 2 minus 1. So basically, you start halfway into your list, right? Everything past that point is a leaf, and this current index, this initial current index is the first or the last node that has a child, right? So the parent of the last node. So starting with that current index, that's how you initialize current index. While current index is greater than or equal to 0, so while you're not at the root, you set the working index to be the current index, and you bubble down as necessary to enforce the heap invariant from the working index. So you set the working index to be the current index, and then you start from there and you say, okay, calculate the left and right child of my working index. If I have left and right children, do the bubble down procedure, right? If I have at least one child, find out which of my children is smallest. If the invariant is broken, swap with that child, set the working index to be that child's index, and keep working toward the bottom of the tree, right? And then once you've bubbled down from the your initial current index, then decrement current index and do this again. and keep doing this, basically starting, working your way up to the root, bubbling down and fixing the invariance as necessary. It turns out that this operation, this algorithm, will in fact build a heap in order n time. And again, the analysis for proving why it will always be order n is a little bit complicated, but it basically has to do with the fact that as you work your way toward the root, the number of levels that you could bubble down starts to grow, but the number of nodes that might need to bubble down that gets smaller, and so overall you can actually prove that you could build a heap in this algorithm in order n time, that it will all average out to be order n time. So I'm not going to do an example of an efficient heap build, but just to kind of to just describe the idea that if you have all your items all at once, you can build a heap from all those items very, very efficiently. All right. So that is the end of today's lecture. And I'm going to be posting these things as we go along. We actually have to make up some time because of the extra spring break. So we're going to end up having more than 2 lectures per week. This week, obviously, we have the midterm. So I'll post another lecture sometime later this week. I won't expect you to view it until after the midterm, possibly. But basically, I'll post these things as online at least a day in advance of our next class period, and then we'll use the class period as a way for people to ask questions and go over the material of whatever was posted from before between the last class period and the next class period as a Zoom meeting. So again, this is all very very new and different than we've ever done before. So bear with me and be patient. I'm so sorry that my daughter's boyfriend cannot stop texting her during during this whole thing. I probably should have told him that he was not communicating with her this whole time. But we'll see. Next time when I use the pad, I'll be sure to turn all the notifications off. All right, thanks.